Okay, in this video, we're going to show you how to do some similar problems that are on homework for chapter 1.4. So we do have some answers here for you, so you can test yourself, see if you're getting them right. But I'll show how to do one or two of them in each section. So here we have a z-score of -2. And you want to find out what this x value is, this actual score is. So we get x equals mu plus z times theta. That was the formula we derived in class. So mu is 100. You can tell that from up here, right? Assume normal, mu 100, just the mean, and standard deviation 10. So plus -2 times sigma, which is 10. Okay. Well, this is 100 minus 20 equals 80. Didn't have to use the calculator for that one. Okay. Let's look at another type of problem. Using the 68, 95, 9.7 rule, okay, let's say we wanted to find 95%. Well, that's within 2 standard deviations away, right? So that would be this 80, and it would be 120. Okay, so that's why we put 80 to 120 here. Notice this is 1 standard deviation away. Should be a comma. So that would be between 90 and 110. And 3 standard deviations away would be between 70 and 130. Okay. All right. Well, here this one we want to actually convert from data point to z-score. So this is the other formula. It's actually the first formula we learned. So z equals your data point minus your mean divided by your standard deviation. So here our x was, well, here our mu is 125, that's our average, and our standard deviation is 30, and our x value is going to be 100. So we're going to get 100 minus the average, which is 125, and we're going to divide all that by sigma, which is 30. Now keep in mind, this is less than the average, so we are going to expect a negative z-score, okay? So we have minus 125, or minus 25, I'm sorry, divided by 30. So this is a number a little bit less than 1. Let's go ahead and turn on our calculator. So we get -25 divided by 30. That gives us -8.833. Okay, go to 0.83. Okay. Going down, it says if the scores are normally distributed with 125, 30, if the upper 20% gets a score of an A, wants to find out what the z-score is that corresponds with that, right? So z-score that corresponds to that, let's just erase this. We're going to do the inverse norm. We're going to do z equals inverse norm. Okay. So this is the upper 20%. So let's just recall, see how this works. If we had a normal curve, okay, the upper 20% is going to be up here. All right, this is going to be some z-score. But the calculator for inverse norm only does area to the left. So it's going to be 1 minus 0.20, which is going to equal 0.80. So notice the two add up to 1, right? All right, so inverse norm. 0.80. And because it's z-score, I don't have to put the 0 and the 1 in, or I could add them. So notice this is the same thing as, so for z-scores, that 80% tile is going to be the same no matter what your data set is. So here, let's do second vars. We got option number 3. The area is going to be 0.80, and mu 0 and 1 are my defaults. Okay, so that's going to have a z-score of 0.84. Okay. So we could do two things. We could use our formula to convert that into a test score, right? So you see here mean plus z times standard deviation let's actually see how that works out. So we'll have our mean was 125 plus our z-score we just found to be 0.84. Now we did round, so it might have some error. Times the standard deviation, which in this case was 30. Okay, so if I could compute it this way, I get 125 plus 0.84 times 30. Okay, so 150.2 round to the nearest whole number would be 150. Now I'm claiming that this is also equal if you did the x equals the inverse norm of 0.80, but now if you put in your mean and standard deviation, you should get the same answer. Let's go to our calculator. Second vars, inverse norm. Let's go ahead and put in 0.8 is already there. Mu is 125 and sigma is 30. Okay, paste that in. There we go, same answer, 150.2. That's good to see that those are the same. Okay, so now we're asked to find some probabilities of z-scores. See the first answer given to you there. Let's see how maybe we calculated this one. So we're dealing with z-scores, so our upper and lower bounds be at least 4 standard deviations away. I'd probably just pick a pretty small number, a pretty big number. Dealing with z-scores, I usually do negative 100 and 100. So let's keep in mind, I'll draw a little picture, that we have this in the middle is the mean, okay, and then over to the right would be 1.2. Okay, so we're looking for the area to the left. So we're going to need a lower bound, and we'll just use, let's say, negative 100. And we'll use 1.2 as our upper bound. Okay. And then our mean and standard deviation is just 0 and 1. So again, you don't have to put that in the calculator. So let's see what happens. Second vars, normal CDF. So lower bound, we'll just put negative 100. Upper bound, we'll put 1.2. Mu, 0 and 1, that's fine. So that probably, you gotta be careful with that minus sign. So don't do minus, you have to do negative. See if I can pull that back up. Oh. So you gotta actually come in here, hit delete, and use the minus negative sign. I was gonna do the whole thing. Well, I'll use negative 10, that'll work too. Alright, for 0.88. Let's get off that. So 0.88. Okay. And here you would do between two. I'll just show that real quick. So second vars, normal CDF. So if you want to do between negative 1.25 and 1.80. Again, 0 and 1 is going to be our default for z-scores. 0.8584, so that matches up here. All right, this next problem I want to say find z-scores for percentiles. So 45% fall below z. Again, since this is a z-score, it's just inverse norm, and we want to know below anyway. So we already have the area to the left. It's going to be 0.45, and since z-score is all I have to put in. So let's say second vars inverse norm 0.45. And that is rounded to the nearest hundredth, which is 0.13. Okay. 80% falls above. Again, this is z-score that corresponds to 20% below. So this is just going to be the same thing here with 0.20 here. And I'll just go ahead and enter that in. So negative 0.84, so that matches up here. All right. Well, so one reason to do z-scores is we can compare things to data sets. So here we have ACT scores and SAT scores. So it says that J scored a 1750 on the SAT, and Chris scored 830 on the ACT. So who did better, right? So if we convert both of these to z-scores, so again, that's the data point minus the mean divided by standard deviation. So when we convert for J, we get 1.33. When we convert for Chris, we get 2.22. So z-scores are all z-scores, so we can tell that 2.22 is higher than 1.33. So in this case, Chris scored better with a 30 on the ACT than J with a 1750 on SAT. So this is a great example of why it's good to sometimes convert and standardize to z-scores. Josh scored 2,000 on his SAT. What was his percentile? So here, these grades, scores were distributed normally with a mean of 1350 and a standard deviation of 30. So what we're really talking about here then, let's go ahead and draw a little picture. Oh, black's fine. Okay. So we have this normal distribution, and Josh scored 2,000. It's above average. The percentile is the area to the left, right? So what we're really looking for is this area. And we have our mean and our standard deviation right here. So this would be the normal CDF. Lower bound, we'll just pick like negative 1,000. Upper bound, we'll pick 2,000. The mean will be 1350, and the standard deviation 300. Okay. So if I were to put that in my calculator, let's see, second bars. Normal CDF, lower bound, negative 1,000, upper bound 2,000, mean 1350, and standard deviation 300. Okay, so we get 0.984. Did pretty good. About 98%, right? So keep in mind too, I mean, that the mean was 1350 and standard deviation was 300. So he was one standard deviation up from that would be 1650, another standard deviation that would be 1950. And we already said that a large part of that data there is within those two first standard deviations, plus you got everything on the left of that. So that is a reasonable answer. This next one though says what score makes up the top 20%? So let's recognize again that, let's draw a picture. Draw it down here. So the top 20%, well, that's going to be the same score that separates the lower 80%, right? So it's 1 minus 20%. So our inverse norm function only goes to the left. So in this case, we'll do 0.80. Again, put the mean and standard deviation since we're dealing with a actual observation and not a z-score. And go ahead and plug in our calculator. So second bars, inverse norm. 0.80, 1350, and 300. Okay, so 1602. So 20% of the people did 1602 or better, 80% did 1602 or worse. All right, our last one, I'll do one of these quantiles. It says the ACT scores were normal with a mean of 20, a standard deviation of 4.5. Find these quartiles. So let's just take a look at the third quartile. So pretend we didn't see that answer. So remember, the third quartile means that, let's put X here, that 75%, okay, did that or less. So This is really just an inverse norm problem. So x equals inverse norm, 75, and again, 1350 and 300. Turn on a calculator. Maybe second bars. Inverse norm. So we're just changing this to 75. And those are the same. Okay, so 150. So 1552. All right, so I hope you found that helpful and helps you with your homework. If you have any questions, just shoot me an email. Thanks.